Alright, so in this video I'm gonna be explaining this model called deepEventMine, which is this paper end-to-end neural nested event extraction from biomedical text. This paper in 2020. Recent neural net approaches on event extraction from text mainly focus on flat events in general domain, while there are less attempts to detect nested and overlapping events. These existing systems are built on given entities and they depend on external syntactic tools. So they propose an end-to-end neural nested event extraction model named deepEventMine that extracts multiple overlapping directed acyclic graph structures from a raw sentence. On the top of the bidirectional encoder representations from transformers model, our model detects nested entities and triggers rows, nested events, and their modifications in an end-to-end manner without any syntactic tools. Our deepEventMine model achieves the new state-of-the-art performance on 7 biomedical nested event extraction tasks. Even when gold entities are unavailable, our model can detect events from raw text with promising performance. This is an example of flat and nested events from BioNLP 2013. Cancer genetic task. So green and orange denote entities, the red one are event triggers. This is the overview of the deep end-to-end event extraction. The hidden layers are omitted for brevity. We use, due to the space limitation, we omit some unimportant tokens like virus. We use abbreviation to represent triggers, entities, and so you see we have a BERT model, and then we get the entity trigger, and then a row, and then event. For example, these are triggers. Entities are within this color, and row, event, there are different colors. The entity or trigger layer assigns entity or trigger types to overlapping text spans or word sequences in a sentence. We employed the modeling of Sohrab in 2018. Since this enables the extraction of nested triggers and entities at once. This model has the advantage that it can utilize all subwords information inside the target candidate, unlike the NER model of Devlin, that only uses the first subwords of words. Particularly, this layer exhaustively considers all possible spans of a sentence with sizes less or equal to the maximum span size for entities and for triggers. The representation for the span from the kth word to the 11th word in a sentence is this. This is the representation from the span from kth word to the 11th word. So first we are concatenating it, and VI sub j denotes the j subword representation in the ith word. Then for row layer enumerates all trigger argument pairs. For example, it enumerates all trigger combinations, all trigger entity pairs. Since each row is constructed by a trigger and an argument, we first compute the representation of all triggers and arguments detected by the entity or trigger layer. The representations of a trigger and an argument are calculated in the same way. A trigger ranging from the starting teeth word to the end T sub E word is represented with the concatenation of its span representation. Similarly, the representation of an argument can be calculated like this. Meanwhile, the context representation C is obtained from sentence representation of birth layer, and the representation R sub I, this is calculated from its trigger representation V sub T. T stands for trigger, so it is calculated from that. Also, it is calculated from the argument representation and context. You can concatenate with the context representation as well. But this is bias that should be learned. This one as well. This is a weight that should be learned. Those are learned parameters. And yellow here is the Gaussian error linear unit activation function. After getting the pair representation R sub I, we pass it to a fully connected layer with a softmax function to predict the corresponding role type. So this is the event layer. So given the triggers and entities detected by the entity or trigger layer and the role pairs detected by the role layer, the event layer enumerates all combination of role pairs to construct event candidate for each trigger. These event candidates include event with no argument. Each candidate is then classified as an event or non-event. To allow the construction of nested events, we build events in a bottom-up manner. Concretely, we first classify event candidates with non-trigger arguments to obtain a set of detected events. We then repeat the following process of constructing and classifying nested event candidates which contain trigger arguments. So we construct nested event candidates by replacing trigger arguments by their corresponding detected event. The representation E sub I of an event candidate I is calculated from the representation of the trigger, the role, and the nth dimensional embedding of the role U, and all embeddings is this. Again, W sub P, this one, and BP are learnable weights and biases. And similarly for the role, these are weights and biases, because there are also roles that are detected by the role layer. So we include not only roles in the structure, but also those outside of the structure, aiming at choosing the appropriate set of roles from all possible role sets. And you see the F1 score is still, all of them are less than 70%, which shows that there's room for improvement in this biomedical event extraction. These are very important, Genia 11, Genia 13. You see F1 score is very low. And this is the comparison of this model with the pipeline training setting when extracting events from raw text and given gold entities on the development sets. So as I said, we have different things: entity, trigger, role, event. Particularly this one is non-standard.